The year is 2035. Global warming has caused the polar ice caps to melt, causing a rise in sea levels across the globe. Through this time of crisis, while everyone was looking for answers, he took advantage of us. Emperor Matsumoto. He fooled us all into storing all of the world's concrete in one place, just to lock it up all for himself. He believed that we humans are undeserving of concrete and believed it was the catalyst that destroyed the world. His former students set out to put an end to his tyranny. Everyone around the world must pray to Emperor Matsumoto in the hopes that he gives the people concrete to rebuild society. His former students have hidden out at a secret base in order to be free from Matsumoto.
We need to end Emperor Matsumoto's rule. His hoarding of concrete in this time of disaster must end. It begins with researching wood properties. We must first gather the wood.
Okay, so for the test setup for our experiment is our wood specimen, simply supported, loaded with a point load at the midspan. And in order to create predictions of the P max, or the max loading it can take before ultimate failure, we have constructed these diagrams. So first of all, here in the shear diagram, we figured that the max shear at both supports should be P over 2, or half the value of the applied load, and it yields this diagram right here. And from there, we calculated the moment diagram by multiplying P over 2 times half the distance to the point load, which is L over 2, and that yielded us a maximum moment of PL over 4 for our equation, and we will use that in this step right here. So utilizing the bending stress equation, sigma equals M times Y over I, we substituted PL over 4 for M and got this equation, PL times Y over 4I, and manipulating this equation for P, which is load, we ultimately obtained this equation, which is P equals 4 times sigma times I all over Ly to receive our P max.
Alright, so this is our dry wood specimen. As you can see, we got 1.5 for the height, 3.5 for the base, and 24 inches right here. So first we have to calculate I. We did that using the equation B, H cubed over 12. And we got 3.5 for B, 1.5 for H, and 12. So we got an I of 0.984 inches to the power 4. Next, we had to calculate Y, which is the distance to the neutral axis. To do that, we did H over 2, 1.5 divided 2 is 0.75 inches. We used these values right here in this equation right here we derived from earlier. So we got a value for P max of 2830.5 pounds. Alright, so this is our wood specimen that was soaked for 24 hours. As you can tell, the dimensions increased by a factor of 1 over 32 inches, which is slight compared to the values we had before. To calculate I, we used the same equation as before. We got I is 1.0565 inches to the power 4, And then we calculated y using the same formula as before as well. We got 0.7656 inches. We used these values right here in the equation John derived from before to calculate P max, which is 2,747.9 pounds.
Thank you. This will be perfect. Now that we have our wood specimen, we can test the flexural strength of the wood when it is exposed to moisture. We'll test in the structures lab.
Okay, right here we have our three specimens were tested, simply supported with a point loaded mid span.
Alright, so for this first specimen, this was our control wood. So no moisture was added, but we had a moisture of 12% assumed based on the wood handbook. This next specimen right here was soaked for about 24 hours, and when measured, the moisture content was about 50%. And then this very last specimen has been soaked for 48 hours and had a moisture of 100% using the machine. Okay, so all three wood specimens were tested the same exact way with a point load at midspan until failure. So during testing, it was evident that the top fibers of the wood was in compression, while the bottom extreme fibers of the wood was in tension. And throughout the experiment, cracks along the bottom in the midspan started to appear and became more prominent as the loading increased. So therefore, it seems as though the failure mode for all three wood specimen is failure in tension due to the load and the increased cracking. Okay, so according to our data and analysis, as the moisture content increases, the flexural strength of the wood decreases. So according to this graph right here, which shows flexural stress versus flexural strain, this red figure represents the control wood, this blue one represents the 24-hour specimen, and this green one represents the 48-hour specimen. So as you can see, the general trend is basically the loading capacity decreases, and as a result, the flexural strength decreases the more moist the wood gets. However, it is important to note that as moisture content increases, the deflection of each wood increases as well. So the control wood itself had a max deflection of 0.74 inches and was considered the most stiff out of all three specimens. The 24-hour specimen had 0.79 inches of deflection and deflected more than the control wood. And lastly, the 48-hour specimen had a deflection of 0.76 inches, which is considerably less than the 24-hour specimen, but it was still deflecting more than the original control specimen. And we're attributing that due to the fact that the 48-hour specimen had this knot on the very edge that most likely would have contributed to the variable data that we saw. Okay, so right here in this table is our results. So here is our predicted column for the dry, 24, and 48. So when we actually tested it, the results they yielded were 2,084.9 pounds for the failure load for the dry. The failure load for the 24-hour was 1,681.5 pounds. The failure load for the 48-hour was 1,434.1 pounds. And Kareem will tell you our ratios.
This column right here represents the actual value divided by the predicted value. So for the dry specimen, we got a ratio of 0.7366. For the 24-hour soaked specimen, we got a value of 0.6119. And for the 48-hour soaked specimen, we got a value of 0.557.
Alright, so as Kareem said, these are our actual and predicted, and the two, which is dry and 24-hour, had decent ratios, but as you can see for the 48-hour one, it had a 0.557 cent ratio, which possibly could be attributed due to the specimen, which we mentioned earlier, which had a knot on its end, and meaning it could possibly be an outlier in this data set due to its imperfection.
With mass flooding occurring all over the world, wood structures will soon become obsolete. In order to mitigate the effect of moisture in wood, we must add sealants to every piece of wood exposed to high levels of moisture, which is costly. Ultimately, to create a better society for the future generations, we need to utilize all the resources. We will change Emperor Matsumoto's rule over concrete and give it back to the people.